I'd like to talk about recycle reactors. So recycle reactors are when you take some of the output from your reactor and feed it back into the input. And you would want to do this. This is commonly done for autocatalytic reactions, for if you want to maintain isothermal conditions, and this is also really common in biochemical reactions. So the hardest part of looking at recycle reactors is keeping track of all of your different balances that you need to do. And so I think the easiest way to do this is to draw a picture. So basically, so if you have let's assume that you have a PFR, a plug flow reactor, and so you have a stream coming in that's, say, FA naught, FB naught. You have a certain volumetric flow rate, etc. And then you have a stream coming out, and this is going to be, well, I'll just draw so you have a stream coming out, and coming off of this, you'll have another stream that feeds back in like this. So then you can call this, say, point Q, and this P. And so then you can start naming some of these streams. So you have FA naught here, and then this stream, so this one here will be this plus this, and I'm going to call that FA1, FB1, etc. And then you have, so then you also have, so your stream coming out here, so you have FA1 here, and then you have a stream coming out here, and I'm going to call this one FA2, FB2, etc. And then the stream coming out is going to be this minus whatever is feeding back in. And so I'm going to call this FA3, FB3, etc. And then this stream coming back in, you have, I'm going to call this R, so basically the recycle stream. So this would be FAR, FBR, etc. And then you have, so V naught here, so then you would have VR for this stream. And so then you also have, you'll have two different conversions. You'll have the overall conversion, which is taking into account everything, and that's X naught. But then you also have a conversion for just the from basically here to here, and I'm going to call that XS. And I'll get to XS and X naught a little more in a minute. So the first thing I want to define is the recycle parameter. So that's going to be defined as R, and R equals FAR over FA3 equals FBR over FB3, etc. So this is basically the ratio of what you're feeding into the stream versus what's exiting. So then I already mentioned the two different conversions, so I'll just write what they are real quick. So first of all, you have X naught, which is equal to, so X naught is the overall conversion, so overall conversion, and that's equal to moles of A reacted over all over moles of fresh feed. And then you also have XS, and so XS is the conversion per pass. So the conversion each time you pass through the reactor. And so that's equal to moles of A reacted in a single pass over moles of A fed. So part of analyzing this reactor is, first of all, defining these different things, because there's more going on here than what we've been looking at in the previous reactors, and so we need to look at, okay, well, how much is reacted here? What's the overall reaction? So, and this, looking at this recycle parameter. So it's part of this is just sort of defining everything, and then just this reactor takes really good bookkeeping. It's really easy to get confused, and so it's just keeping track of what all your different parameters are, and that's why having a drawing is really helpful. So the first thing we want to do is write some equations for what the output streams are, so FA3, FB3, for what this stream is, FA2, FB2, and for what the recycle streams are. And then once we do that, we can do a stream balance at point P and also at point Q. So I'll go ahead and I'll do this output stream first. So we know that FA3 is equal to, so we know that this is FA3 and FB3, the streams out here are the overall conversion. So we already know what the overall conversion is. We know that that would be FA naught 1 minus X naught, because we're looking at X naught here, not XS. And so, and we also know that FB3 would be equal to FA naught theta B minus B over A X naught, and then just etc. through this. And then we know that FA2, so these are together, is equal to, and we know that at FA2, then the conversion has been this XS, the conversion per pass. So we know that that would be FA1, and so that's FA1 right here, 1 minus XS. So we're looking at the conversion from here to here for FA2. And then for FB2, this is equal to FB1 minus FA1 B over A XS. So these are together. And then we can get these, the recycle streams, the FAR, FBR, etc. from the definition of R. So we know that FAR is equal to R FA3, and that's from here. So FAR is equal to R multiplied by FA3. And then we already know what FA3 is, so we know that this is R FA naught 1 minus X naught. And then we can do the same thing for FBR, so that would be R FB3, and that's from this R, and we know what FB3 is, so R FA naught theta B minus B over A X naught. And then assuming what you have in your feed, like if you have C and D also, you should, from this, you should be able to figure out how to write those equations as well. So the next thing we want to do is a balance on the stream intersections, so at P and Q, because now we have equations for FB for this output. We have equations for the output right here before it splits. We have equations for the recycle. We know what FA naught and FB naught are, etc. So we should technically know FA1 and all those. So we should be able to do the balance now at P and Q. So I'm just going to erase some stuff real quick. All right. So first of all, I want to do the first balance at point P right here. So P, and we know that FA naught, well, we know that FA1 is equal to FA naught plus FAR. So I can write that. FA1 is equal to FA naught plus FAR. And then we know what FAR is because we derived an equation over here. So we know that this is equal to FA naught plus R FA naught 1 minus X naught. Then we can pull the FA naught out. So then this is FA naught 1 plus R 1 minus X naught. And then we can do the same thing for FB1. So we know that FB1 is equal to, same thing, FB naught plus FBR. So FB naught plus FBR. And then from stoichiometry, we can write an equation for FB naught to relate it to FA naught. And we know what FBR is, so we should be able to get that. So we know that FB naught is equal to FA naught theta B minus B over A X naught. And then this is plus FBR, so this R FA naught theta B minus B over A X naught. And then we can pull out the FA naught and combine some things. And if we do that, we get the FA naught is, oh, whoops. We get the FB1 is equal to FA naught multiplied by theta B plus R theta B minus B over A X naught. All right, so at point Q, we know that FA2 is equal to FA3 plus FAR. So FA2 is equal to FA3 plus FAR. And then we already know that FAR is equal to R FA3, and that was from the definition of the recycle parameter. So this is equal to FA3 plus R FA3. Just to remind you, this R FA3 is from this R is equal to FAR over FA3. So I just plugged this, like I just multiplied the FA3 over and then put that into there. So then I can pull out the FA3, and if I do that, I get well, Fa3 1 plus R, and then from previously I already know that Fa3 is equal to Fa naught 1 minus X naught, so then this equals Fa naught 1 minus X naught 1 plus R. And then if I do a similar balance for FB2, I get R plus 1 Fa naught theta B minus B over A X naught. The next thing we want to do is relate the molar flow rates. So I'm going to go ahead and put V naught 1 right there. So then we know that this V naught 1 is equal to V naught plus VR. So we know that V naught 1 is equal to VR plus V naught. And VR is equal to R Ft naught over Ct naught 1 plus epsilon naught X naught. And this is equal to V naught R 1 plus epsilon naught X naught. And Ct naught is equal to CTR, which is equal to P naught over R T naught. So then if I plug this into here, I get that V naught 1 is equal to V naught 1 plus R 1 plus epsilon naught X naught. So you can relate the volumetric flow rate in the reactor to the volumetric flow rate entering the reactor. So V naught 1 in the reactor to V naught entering with the following relations. So V naught is equal to V naught 1 plus epsilon S X. And then we can plug this in for V naught 1. So if we do that, we get this is equal to V naught 1 plus R 1 plus epsilon naught X naught. So I'm just plugging this in. And then 1 plus epsilon S X. And so X in this equation is the number of moles reacted per A entering the reactor. So epsilon S is equal to YA1 delta, which is equal to FA1 over FT1 delta. And we've already derived a relation for FA1, and using the same concept, you should be able to derive a relation for FT1. So doing that, this was, well, FA1 was FA naught 1 plus R 1 plus X naught delta over Ft naught 1 plus R 1 plus epsilon naught X naught. And then this is equal to YA naught delta 1 plus R 1 plus X naught over 1 plus R 1 plus epsilon naught X naught. The next thing I want to do is find the molar flow rates. So FA, FB for basically the entire system. And then from that you can find CA and the equations that you need for your rate loss so you can solve this. So I'm going to erase some stuff. So at this point we've pretty much defined all of our feeds and all of our parameters, and so now we can start writing the equations we need to actually solve the problems. So first of all, we want to find the molar flow rate of A, so FA, and that's equal to FA1 1 minus x, and we already found an equation for FA1, so if we plug that in, then this is FA naught one plus R 1 minus x naught multiplied by 1 minus x. And then we can also write an equation for FB. So we know that FB is equal to FB1 minus FA1 B over AX. And then we know what we already derived an equation for FB1. We already derived an equation for FB1 and FA1, so we can plug those in. And if we do that, we get the FB is equal to FA naught theta B plus R theta B minus B over A x naught minus B over A FA naught 1 plus R 1 minus x naught x. And then to get CA, we know that CA is equal to FA over V, and so we just got a relation for FA, so we know that FA is equal to FA naught 1 plus R 1 minus x naught 1 minus x, and this is over V naught 1 plus R 1 plus epsilon naught x naught 1 plus epsilon s x. And this is from our expression that we found earlier for V. So then from here, we can write a design equation for this. Equation for a PFR would be, so I'm going to write mole balance. V is equal to FA1 0 XS dx over minus RA. And so for this, we're looking at the conversion from here to XS. Then we can just do the same thing we have been doing. So rate, because we need the rate, so minus RA is equal to K, and then it's probably a function of CA, CB, etc. And then you would do your stoichiometry, which we've already gone through all that. I want to go through a few other relations just because there are a few different ways you can solve this and a few different things you can look at. So I'm going to erase some stuff real quick. So the first thing I want to look at is the relationship between XS and X naught. Look at FA, then FA is equal to FA1 1 minus XS and this is equal to FA naught 1 plus R 1 minus X naught. And then we know that FA1 is equal to FA naught 1 plus R 1 minus X naught. So we can plug this into here. And then we have a relation that has both X naught and XS. So if we do that, then we get, well, we get FA naught 1 plus R 1 minus X naught 1 minus XS is equal to FA naught 1 plus R 1 minus X naught. So if you solve this equation for XS, you get XS is equal to X naught over 1 plus R 1 minus X naught. And then one thing you should notice right away is that if R is 0, in other words, if your recycle feed is 0, then XS is equal to X naught. So if R equals 0, XS is equal to X naught. So something else you might be interested in is what your concentration is here, because we found our concentration for basically the entire thing, Ca, but we might want to just know what the concentration is here. So that would be Ca1. And so for that, first of all, we want to start with the equation. We already know what Fa1 is because we found it earlier. So Fa1 is equal to Fa naught 1 plus R 1 minus X naught. And so then to get Ca1, you should just be able to divide Fa1 by V naught 1. And so then this is equal to Fa naught 1 plus R 1 minus X naught over V naught 1 plus R 1 plus epsilon naught X naught. So I'm going to erase some stuff real quick. So another parameter you might be interested in is getting your conversion here. So that would be XA1. So we found the conversion for the single pass, which was XS, overall, which was X naught. And so if we want to find a conversion for XA1, and I'm not going to go through the entire thing because this is your homework problem, but if you, basically to do this, you need to do a mass balance at this point. I'm going to take a step back real quick. If we look at what these two conversions actually are, so for instance, X naught, let's erase that for now. X naught is equal to Fa naught minus Fa3 over Fa naught, and XS is equal to Fa1 minus Fa2 over Fa1. So X naught is basically the conversion from Fa naught minus what you have left divided by Fa naught, and then the pass is just over the reactor, so over these points. So for XA1, this is F A naught plus R Fa naught. So this is what's in the feed plus what hasn't been converted that's coming back, minus Fa naught plus FAR over Fa naught plus R Fa naught. And then we know that we already found a relation for FAR. We know that that's equal to R Fa naught 1 minus X naught. So then you can plug this in and you should be able to find a relation for XA1. And since you already know what the relation is, I'll just write it down because I want to apply that to the mole balance equation. XA1 is equal to R over 1 plus R X naught. So then if we look at the original mole balance, so V is equal to FA1 0 XS dx over minus RA. So we can actually rewrite this so that there's some conversion using these relationships. So if we do that, we get, well, we get V is equal to R plus 1 FA naught XA1 to XA2 dx over minus RA. And we know what XA1 is because we just found it, and we know that XA2 is X naught. So then we can write that in. So V is equal to R plus 1 FA naught R over R plus 1 X naught, this is X naught here, dx over minus RA. So then I'm just going to summarize these two equations real quick, because you can use either one of them to solve this problem. You just need to make sure that depending on which one you use, you're using the right concentrations in your rate loss. So we have the mole balance, and so we had V FA1 0 to XS dx over minus RA. And then for the second one, we had V is equal to R plus 1 FA naught R over R plus 1 X naught to X naught dx over minus RA. So in order to solve this problem, you would pick one of these, and then you would write your rate loss. So rate, and then say it's minus RA K CA, or it could be K CA squared. For your stoichiometry, you just need to make sure that you're using the correct form for whichever equation you're using. So I'll just say this one's 1, this one's 2. And you can choose either one. You should end up with the same solution. So for instance, let's say you do number 1, then your stoichiometry would have to be this full equation that we derived earlier that was over basically the full reactor. So CA was equal to CA naught 1 plus R 1 minus X naught 1 minus x over 1 plus r. And so then if you're using number 1, then you would just plug this into whichever rate law you're using and then plug it into your equation and integrate. But if you were, say, using number 2, then your concentration would be Ca is equal to Ca naught 1 minus Xa. And this is actually Xa. And so then once you integrate, this is, if you're using, say, this equation where you have the xs, this is, because you're integrating to xs, this is where you need the relation for xs to x naught. So once you integrate that, then you would plug in, you know that xs is equal to x naught over 1 plus r 1 minus x naught. And then for both of these, we can put this in terms of concentrations, Ca naught and Ca3, by looking at the definition of x naught. So we know that x naught, and I wrote this down earlier, but I erased it. We know that x naught is equal to Ca naught Ca3 over Ca naught. If you wanted to get your final answer in terms of concentration, you would substitute this in for x naught.